Hello, young scholars. Sorry to be missing you. Today we're going to learn about how to handle motion when it's in more than one dimension. Up until now, maybe you noticed, maybe you didn't, every single thing we studied that was either moving in a straight line, like a car moving horizontally, or in a straight line like something going up and down like a rocket, but always only in one dimension. What do we do when we have motion in two dimensions? In other words, what do we do when we perhaps are moving at 4 meters per second to the right, but simultaneously a wind maybe is blowing us at 3 meters per second upward? How do we figure out what kind of motion we get in that case? Here we must introduce a new mathematical idea, and that is the mathematics of vectors. What is a vector? A vector is anything that has a direction associated with it. So quantities like velocity, acceleration that we've studied all have directions associated with it. Previously, it was okay to just call the direction either positive if it was moving to the right, or maybe negative, left, positive if it was moving up, negative if it was moving down. But now we have to be a little bit more careful in how we talk about directions. So things like velocity, acceleration are vectors. Also displacement, the idea of how far you have gone from some other point, is a vector. Other quantities, things like time, has no direction associated with it. 10 seconds, 15 seconds, but there's no direction associated with time. Same with the word distance. How far you have gone is a little bit different than what direction you have gone from some place. That's what displacement is. Speed also is just how fast you're going without regard to direction. So these quantities here are called vector quantities. These have a different name. These are called scalars, S-C-A-L-A-R-S. There's some other quantities that we'll encounter in the future that are vector quantities as well. Things like force and momentum are also vectors. They have a direction associated with them. So how do we handle it when we have two vectors that are happening simultaneously? How do we add 4 in the x direction plus 3 in the y direction? That is what we need to learn. And we begin here with the very first steps of vector mathematics, which you should know. Vector mathematics is a long and deep vein in mathematics. It goes all the way through vector calculus and beyond. We're just starting at the very first step of vector addition. How do we add 4 meters per second to the right plus 3 meters per second up? The answer is pretty interesting. To add two vectors, you simply assemble them in an additive fashion, and what you're seeing right here is how two vectors are added. Notice that the tip of one vector is touching the tail of the other vector. To a vector mathematician, that picture looks like addition. When you add those two vectors together, you get a sum of those two vectors that looks like this. It starts at the beginning of the first vector, goes to the end of the second vector, and that vector right there, that red one, is the sum of those two vectors. In fact, there's a special name given to the sum of two vectors. It is called the resultant vector. 3 plus 4 in regular mathematics is 7, and we call 7 the sum, but 3 plus 4 in vector mathematics could be a lot of different answers. In this picture, we can figure it out nicely because we have a nice right triangle, and so we can apply the Pythagorean theorem to figure out the length of the hypotenuse. You recall a squared plus b squared equals c squared. So if we perform that operation with these numbers, we get 4 squared plus 3 squared. That's 16 plus 9 equals c squared. C squared equals 16 plus 9, so c squared is 25, so c equals 5. This is the familiar 3, 4, 5 right triangle. So that means that if you're traveling along 4 meters per second this way and being side pushed 3 meters per second this way, the resultant vector, your resultant speed, your actual ground speed, would be 5 meters per second. Here's another addition of 4 meters per second plus 3 meters per second, and we'll see we get a slightly different answer, a slightly different resultant vector. Again, notice that the vectors are added together tip to tail. That shows that we're adding 2 vectors, and the resultant, again, is another vector from the beginning of the first to the end of the last. How long is that vector? Well, it's longer than just an ordinary 3, 4, 5 triangle hypotenuse. To figure out its length, you would have to know something about the other 2 vectors. If the 4 was drawn to scale, in other words, it was drawn 4 units long, and the 3 was drawn to scale, 3 units long, we could use the same scale and measure this. Estimating, you can see it's more than 5, but it's got to be less than 7, so maybe perhaps if we measured it with our ruler using the exact same scale, maybe we'd find out that it was, oh, I don't know, maybe 6.2, let's say, meters per second. But you'd have to draw it out very carefully and make sure everything was measured perfectly. Here are some interesting properties of adding vectors. Notice that it doesn't matter whether you add the 4 to the 3 or the 3 to the 4. We could have started at first with the 3 vector and then added it to the 4 vector, and notice that still shows addition there. And regardless of the order that you add them, the resultant vector still will represent a shortcut from the beginning of the first to the end of the last. So vector addition does not depend on order. The other thing you should notice is that you can move a vector around anywhere that it suits you on the paper that you're working on, so long as you don't change its length, because that would change the fact that it was 3 meters per second long, and also you can't change its direction. That would mess things up as well. But otherwise you can slide the vector around wherever you like to help you add vectors together. So, for example, supposing we had these 3 vectors to add together. Right now they're not in an additive situation. We have all their tails touching together, but we can, if we wish, move any vector we like and put them together so that they are adding. So here's vector 1, here's vector 2, and here's vector 3, all added together, and the resultant vector, the sum of those 3 vectors, would be a vector which begins at the first one and ends at the second one. Oops. So if you're describing a vector, you need to describe 2 parts about it. You need to say how long it is. You'll notice here that this R value tells us how long this one is. It's 14.8 units. Maybe those are in meters per second squared or something. You have to say how long it is. That's called its magnitude. And you have to say what angle it's pointed at. Look at the angle marker up here, and you'll notice that when I'm aligned with the x-axis, that's 0 degrees. And so by standard definition, we rotate the angle like this. We get to 90 degrees when it's vertical, 180. That's the standard way that you measure the angle of a vector. Notice that if you go below the 0, you could use a negative angle in that direction. You can also use the positive, and when you get to here you can say 180 degrees. You could say also 185, 190, and so on. Or you can use the negative, but always the 0 is your reference for measuring its angle. Let's add a couple more vectors here again. Here's a vector. It's got a magnitude of 17.1 and a direction of 20.6 degrees. To that we'll add a second vector whose magnitude is 12.7, pointed at an angle of 135. To add them together, you simply assemble them tip to tail, and the sum is called the resultant vector, and there it is, and you should see that it kind of completes the triangle, but notice here we've got tip to tip, and here we have tail to tail. We're not adding the resultant vector, we're just adding these two. That's addition, and this green one is the shortcut from the beginning of the first vector to the end of the last. It also has a magnitude of 16.6 and an angle that looks like it's at about 65 degrees. So, to be clear, the magnitude is how big the vector is. For example, this displacement vector is 100 meters, and the direction is the angle relative to the x-axis. That's the standard way you measure angles in math and also in vector mathematics. One more example of vector addition. Here's 3 vectors. I'm going to leave one of them still and add the other 2 together. There they all are added, tip to tail, and so the sum, the resultant vector, should be a vector that starts at the beginning of the first and ends at the tip of the last. These 3 vectors added together should equal that one. And the order you add them should not matter. We should get the same resultant vector no matter how we add them. We could have also started with this guy first, this guy second, and that guy third, still same resultant vector.